Hello, everybody, and welcome to Lecture 6 on Chapter 10 for our Critical Thinking course. This lecture and my handouts aren't sufficient for understanding important material in Chapter 10, but they are necessary. You must also read and use the text as you work through the exercises and quizzes. See especially my Chapter 10 handout on causality and Mills methods, and my summary about causes in Module 4. Also, review the short videos I provide links to in Module 4. Brief review. Recall from Chapter 1, I described two kinds of rationales, an argument and an explanation. Rationales are anytime we give reasons that support conclusions. One kind of rationale is called an argument that's designed to convince us of the truth of a conclusion by giving reasons which are evidence for accepting that conclusion. And I contrasted this with explanations, which are rationales also, but these are designed to help us understand a fact or event by giving reasons specifying its causes. So explanations and arguments function differently. They look similar. Both have reasons, both have conclusions, but they answer different questions. In this lecture, I'll talk about in general, the concept of causality. It's a very complex idea. We'll talk about Mills' five of his methods, limitations of those methods, the relation between theoretical and experimental science, the notion of inference to the best explanation, which is a kind of induction, and I'll talk a little bit about hypothesis testing, experiments, and predictions. Say a lot more about that when we discuss Chapter 13. Let me say something about causality. Alleged cause-effect relationships between events or things involve many factors. When we say the rock broke the window, to understand this, we have to know something about the weight of the rock, the velocity with which it's thrown, the angle it strikes the window, the density of the window, the rock of course, and the strength, perhaps, of the window in such a way that it might resist breakage up to a certain point, and then of course it shatters. Any causal network of factors or variables is that set of conditions that bring about an effect. Some ways of describing these you'll come across in the literature. There's the normal state, that's the historical information regarding an object. So the rock remains at rest unless something moves it. The window remains intact unless something breaks it. Abnormal state, that's this drastic change in the normal state regarding an object, the window now being broken by the rock. We also talk about the precipitating or proximate cause. That's the object or event directly involved in bringing about an effect. There, of course, are other factors. And a remote cause is going to be anything that is connected to the precipitating cause by some chain of events. A causes B. Such statements are ambiguous unless the context is specified clearly. This is because the term cause is vague. There are at least three senses in which one might intend to be using that term, and we always have to clarify. In the absence of the person being able to give us more detail, we have to basically consider all of these possibilities. We could consider a cause as a sufficient condition or a necessary condition, or both a sufficient and necessary condition. Recall that we talked about this a little bit in Chapter 1. So you have to interpret the term cause in either of these three ways. The most charitable way to interpret A causes B is to say that A is one way to produce B. And there might be other ways, but even that has exceptions as well. So here are some examples. A is a sufficient condition for B. That is, A is enough to make B happen. As in, electrocution causes death. There are other ways we can cause death. Electrocution isn't the only way, but it's a way which will be a good enough way to cause that outcome. A is a necessary condition for B. Here the term necessary is a way of saying that A is essential for B to happen. That is, without A, you can't get B. So we say clouds cause rain. You never get rain without clouds. And finally, some combination of the two is going on often. A is both a necessary and sufficient cause for B. And we see this in precise scientific statements, for example, in physics and chemistry and biology. Here's a claim. Force causes a body to accelerate. Force is both necessary and enough to make a body accelerate. So the rock being tossed through the window, in that case, the rock is going to be at rest unless some force acts on it. The window won't break unless something acts to shatter its integrity. So how do we use causal factors? Here are two ways. If you want to avoid or prevent an effect, E, then you should block any necessary condition for E, since E can't happen unless the condition, the causal factor, happens first. For instance, if you want to avoid catching a virus, then you reduce your exposure to virus particles, which cause illness. So you wash your hands, stay 6 feet away from people, wear a mask, get vaccinated, etc. If you want to produce an effect, then you should satisfy a sufficient condition for E, and there might be multiple conditions. For instance, if you want to have $1 million when you're 60 years old, then you take advantage of compound interest and you invest $10,000 per year in the stock market in an S&P 500 index fund with an average annual rate of return of approximately 7 to 12% for 35 years. This is the recipe for becoming a millionaire in 40, 45 years. $10,000 sounds like a lot of money, but when you get out of college, you should make 2 to 3 to 4 times as much on average as you make now as a student. Just do it. Okay, here's another example. Breathing elevated ozone levels causes vulnerable populations, such as the elderly and persons with diabetes or heart disease, to be at heightened risk of asthma, heart attack, stroke, and sudden death from arrhythmias. Here, it is the inhalation of ozone, which is a major component of photochemical smog. The inhalation of ozone is a sufficient condition for asthma, heart attack, stroke, etc. It's not a necessary factor, since other factors may also be enough to provoke these ailments. This causal claim does not assert that inhaled ozone always provokes such responses, only that it is sometimes enough to cause them, or it's often enough to raise the probability of these sufferings. Brief review from Chapter 1 again on explanations and arguments. Again, they're not the same thing. They look similar. Both have conclusions, both have reasons, but they do different things. Explanations should have a logical structure and a reliance on evidence, just like we find in good inferences, arguments. But there are too many exceptions for us to conclude that only arguments are explanations, or that all explanations need to be just like arguments. We want to see how science explains phenomena, appearances, things we observe. But we need first to understand the difference between arguments and explanations. The best way to do this is to, again, consider the distinct function of each. So review the diagram that I gave you previously so that the difference between arguments and explanations becomes clearer. Now, the thing about explanations is that they specify causes, likely causes, probable causes. But we must say more about what causes are and the language we use to describe causal reasoning about cause and effect. A causal claim is a statement that asserts that one event causes another, or it's a factor in the provoking of another event. Consider this explanation. Jack has the flu because he inhaled flu virus particles from other people sick with the flu. The causal claim here is that virus particles cause the flu. So if you want to explain why Jack has the flu, the explanation is he inhaled flu virus particles from other sick people. A causal hypothesis is just a causal claim, that is a claim about something causing something else, usually but not always called a hypothesis because it is speculative. It needs to be tested, as all causal claims and any claims should be before we accept them. In general, a hypothesis can be a description such as Jack has the flu, or it can be an explanation. A viral infection makes Jack sick. A hypothesis can describe or explain an observation, an event, or even explain correlations between factors or events. In fact, we're going to say more about that. A causal hypothesis explains or describes the likely cause of whatever we observe and want to account for. So let's calibrate the language a little bit. We're familiar with the term correlation, and correlation is equivalent to the term association, which is equivalent to the term link. So you can use correlation, association, link interchangeably, at least scientists do. But none of those terms implies or is equivalent to the term connection. The term link is too vague, I think, so I avoid using it. It sounds too much like connection. Obviously, some connections are links, but it isn't the case that all links are connections, because a link could just be an association between factors that we find correlated. They may have no relation whatsoever. Every causal hypothesis requires a controlled observation of a clear correlation. And it requires a logical argument for accepting that the causal hypothesis, explains the correlation. If there is no observed correlation association, then there is no connection. And I'll give you some examples shortly. A causal argument then provides evidence for accepting a causal hypothesis. That is, a causal argument provides reasons for accepting some particular explanation. A causal inference, reasoning about cause and effect, is an inductive argument about causes and effects. I want to be clear here. Causation is a relation between events. Causation is not the same thing as implication. Implication is a logical relation between propositions. Never confuse logical implication with event causation. They are separate. Causation is a relation between some events. Implication is a relation between some propositions. Confusing the two amounts to not understanding the difference between explanation and justification. So again, review skill 3 on the basic skills handout. I talked about this. Lots of correlations are accidental. Nevertheless, correlations are suggestive and useful for generating testable hypotheses, those which we justify accepting by observations and controlled experiments. So here's a more detailed example of a basic causal argument. We have claims 1 through 6. Jack is not feeling well. He has a fever, chills, muscle aches, cough, congestion, runny nose, headaches, and fatigue. Those are his symptoms. Number 2, Jack tested positive for a viral infection on a rapid influenza diagnostic test of his nasal secretions. Number 3, lots of people infected with the flu virus have fever, chills, muscle aches, cough, congestion, runny nose, headaches, fatigue, and test positive. So this is our hypothesis. It describes a strong correlation observed between typical symptoms and viral infection. The more these symptoms are present in a group of people, the more we see viral infection diagnosed. So we start thinking maybe there's some connection. That is, the one might be causing the other. That is, the virus particles might be causing the infection. Up until very recently, I'd say in the last 100 years, this was not obvious, that these invisible particles actually caused disease. Number 4, if a person has typical clinical symptoms and tests positive on an RIDT, then X has a viral influenza infection, which is causing their symptoms. This is going to be our general causal principle for explaining correlations. X is a probable cause of Y only if X and Y are strongly correlated and no better alternative explanation of the correlation is available. This assumption, stated or not, is always essential, always implied, presumed in any argument about something being the cause of something else. So if you're going to say X is a likely cause, a probable cause of Y, you've got to include something like this. There's this strong correlation, and nothing better explains it. It isn't accidental. 6, Jack's symptoms and test result then are caused by a virus, a flu virus. So the causal hypothesis here is what explains Jack's symptoms and test results. Recall that constructing an argument for evaluation requires clear, precise statements of reasons presented in a logical form that justifies accepting a specific conclusion. I've been talking about this a lot in discussion where I'm asking people to reconstruct arguments. It's absolutely essential you get the reconstructions right, otherwise you will fail to understand and test effectively any argument. It's important to realize that a causal hypothesis actually explains correlations. So what are you doing with explanations? You're actually explaining correlations, apparent connections, associations. Causal claims aim to describe the most likely cause of an observed association between two or more events or factors. In this example, we want to explain Jack's symptoms, and this is what the conclusion is doing. So in explanations, the conclusion is explaining the alleged facts. Notice that the causal hypothesis occurs in the conclusion, claim 6. In our example, all of the other statements express reasons for accepting that conclusion. Notice also that claims 1, 2, and 3 in the argument above state descriptive hypotheses. They describe what we observe. While statements 4 and 5 express our assumptions about causal relations and how best to explain them. These are sort of general principles. Details about correlations and methods for testing causal claims about them follow. Causal hypotheses then actually explain correlations. They don't directly explain things or events. They explain associations between events, between factors. If you want to explain the association of A and B, where B regularly follows A, one way to do this is to postulate that A is a cause of B. Again, don't be hasty on this. It's possible that what's causing A and B is some other factor. Causal claims aim to describe the most likely cause of an observed association between two or more events or factors. And again, if you're going to look for a likely cause, you've got to consider other possible causes as well and then rule out some. In this example, we want to explain Jack's symptoms, and this is what the conclusion does. In the sample argument 2 slides ago in the handout for Chapter 10 also, notice that the causal hypothesis is in the conclusion, claim 6. So here are some possible ways data, factors can be correlated. So a strong positive correlation, when you draw a line through the data points, it kind of goes from left to right, it increases. You see an increase in frequency. Where the one factor increases in frequency, so too does the other. A weak positive correlation would be some of the data points are more scattered. It's not such a steep curve here. Now a strong negative correlation, again, a negative correlation is where when one factor goes up, the other factor goes down. Right, so the more classes a student misses, as that number increases, we see a decrease in their scores on tests, and we wonder whether there might be some connection. That's an inverse or strong negative correlation. A correlation is a measure of an observed relation between two or more variables. Variables are properties that you measure, control, or manipulate in research. Correlations are associations, but they don't imply connections, none whatsoever. In statistics, a correlation is used to predict the value of one variable given the value of the other. For example, a correlation might relate the distance you commute to work to the number of gallons you consume in your commute. The farther you drive, the more gas you consume. This would be a positive correlation. As your distance increases, your consumption of gas increases as well. Now, all causal arguments require and even imply correlations. If there is a causal relation, then there has to be a correlation. And you really want to be able to observe this. However, it's not enough to observe a correlation and then draw the conclusion that there's a causal connection. You have more work to do. You have to rule out accidents. You have to rule out common causes. You have to rule out that the one factor is actually causing the other in the opposite direction. You can't overlook alternative explanations. You can't say X causes Y unless X and Y are correlated. Here is a chart relating the global average temperature and the number of pirates. Notice on the left that as global average temperature increases, the number of pirates decreases. There are several possible relations, one of which, of course, could be this is coincidental, that there is no connection. Of course, there might be a connection in the sense that the global average temperature increasing might make piracy more uncomfortable. There's another explanation. It could be that the decrease in the number of pirates is due to some other factor. So sometimes actual correlations look significant, even causal, but they are not. A spurious correlation occurs when two events or variables have no direct causal connection, yet you infer mistakenly that they do. And the mistake here is in accepting that the correlation, which is real, we observe an association between factors. We observe that the association happens, and we jump to the conclusion that there's some connection. When, of course, there might not be. It might be accidental. Or it might be that the two factors are explained by some other factor, some previous factor. Something is explaining global average temperature increase, and another thing is explaining the decrease in the number of pirates. I don't know, industrial pollution, human effects on the environment, increasing pollution causes global warming and also is causing less pirate activity. I don't know. Look at the chart on the previous slide. It shows that global average temperature correlates with the number of pirates negatively, that is, as the temperature increases, pirates decrease. Shall we conclude then that a pirate shortage causes the global warming? I mean, that's another way to go if we're jumping to a conclusion. So some correlations are real but meaningless or misleading coincidences. These are called spurious or illegitimate because they look significant but they're not. And what I want to emphasize here is that you don't get to call a correlation a connection until you've considered several alternate hypotheses that explain the same data, explain the correlations. And then you test them. And you only accept temporarily that hypothesis which explains best. This is the method I'll call later inference to the best explanation, where we accept that explanation which explains best of all other explanations available. So it's not spurious because we can imagine that the correlation is silly, or in the case of the pirates and global warming, it might seem just crazy to think that there's some kind of connection. But again, we do that all the time. And so what you want to do is consider every hypothesis against its rivals, and only then accept that hypothesis which remains. A non-causal correlation is spurious, apparent but not really connected, when, for instance, a common antecedent cause produces both X and Y. And this makes X and Y look causally related, but they're not. Again, we can't see this unless we test under controlled circumstances. Other variables or factors, if undetected, may make it look like X causes Y. By the way, it could look like X causes Y, but Y could be causing X. The correlation could be accidental between X and Y. Could also be that some other factor, unknown factor, produces both X and Y. Sometimes when variables correlate, it's due to mere coincidence or the presence of one or more unseen factors called confounding factors. These are factors that confuse us. For example, when ice cream sales increase, we notice so do homicides. But another factor probably explains the correlation better. Warmer weather leads to more ice cream eating and more stressful, lethal social interactions. Identified correlations don't represent causal relationships unless we rule out the spurious relationships. So we want to consider all possible relations, some of which are going to be, spurious. We don't want to jump to accepting those, or any, until we've considered them each against each other. This is why scientific studies must show that the probability of a correlation between two variables or events due to chance is very low. This is something that's referred to in papers as the p-factor, where you want to have a less than, say, 5% chance that it's accidental. And showing you how to determine that is beyond the scope of this course, but in statistics, they will show you how to do this. And we want to make sure it's not due to chance before anyone considers correlation significant statistically. So, brief review, there are different kinds of correlations. A positive correlation is one where property A is positively correlated with property P in a population. If and only if within that population the percentage of A's that are B is greater than the percentage of non-A's that are B. This is a very specific statistical description. Large values of one variable are associated with large values of the other, and small with small. As the value of frequency of one variable in a population goes up, the value of the other goes up. Or as the value of one variable goes down, so does the other. But these correlations may not be actual connections. Some examples. There is a positive correlation between smoking and alcohol use. As alcohol use increases, so does smoking. I'm just presenting correlations here, statements that describe associations observed. That's all. Education and income are positively correlated. The more educated a person is, the higher on average their income is. Not always, not necessarily. We're talking about averages in a population. Smoking cigarettes is positively correlated with having a heart attack among young people. Negative correlation, what's that? Property A is negatively correlated with property B in a population if and only if within that population the percentage of A's that are B is less than the percentage of non-A's that are B. Large values of one variable are associated with small values of another. This is also called indirect or inverse correlation. As the value of one variable goes up, the value of the other goes down. In the case of the pirates and global average temperature increases, we see a negative correlation. Again, they may not be due to any actual causal connections. I mean, they could be, but they could also be accidental. To say that A could be a cause of B is true. At the same time, A could not be a cause of B is true. We have no good reason to accept one possibility over the other until we do some measurements testing. Some examples of negative correlations here. The weight of a car and miles per gallon are negatively correlated. Cars that are heavier tend to get less miles per gallon of gas. Not necessarily, it's an average. School achievement and days absent from school are negatively correlated. People who miss more days of school tend to have lower grade point averages. Vaccinations and illness. The more that people are vaccinated for a specific illness, the less that illness occurs. Realize that links, alleged links between phenomena can be correlations, but not causal connections. That term link is vague, unclear. To say that there exists a link between, say, obesity and cancer might be true, but this implies no causal connection. Only further controlled testing of variables can establish that any link is probably causal rather than coincidental. I mean, we probably should default assume that associations, correlations are coincidental, and then defeat that with some statistical analysis and then consider causal hypotheses. And not just one, but at least three. The reason researchers go so far as to say obesity causes cancer is that not only do they observe strong correlations between cancer diagnosis and obesity in a population, in repeated observations where they control for confounding other factors, they have also induced cancers in obese laboratory animals that they cannot induce in non-obese animals. This is a really important point. In randomized controlled trials, which I'll describe in more detail when we discuss chapter 13, in peer-reviewed randomized controlled trials, we actually make the phenomenon we suspect produced by a specific factor happen as a result of only that factor being the relevant factor in the experimental group versus the control group. So correlations are necessary for causations, but correlations are never sufficient to establish causation. And you've heard this now, I'm telling you why this is the case. For example, extra fat in the body does not just sit there. It's active, sending out signals to the rest of your body. It can affect growth, metabolism, and reproductive cycles. These signals can tell cells in our body to divide more often, which lead to cancer. Here's that example in more detail. So these are examples of three causal factors associated with obesity that contribute to cancer. Now, they're not merely associated by observations where we see correlations. Each of these has been instrumental in lab settings we have made happen. And as a result, subsequently, we induce cancers. After menopause, estrogen made by fat cells can make cells multiply faster in the breasts and womb, and this increases the risk of cancer. Again, what's cancer? It's this unchecked cell division. the cells which usually naturally stop dividing, and some cells actually die, just keep dividing in such a way that their division exceeds the rate at which they are dying. And those cells eventually spread throughout the body in metastasis. Excess fat can cause levels of insulin and other growth factors to rise, which can also tell cells to divide more rapidly. So all these ways of causing cells to divide more rapidly increases the chance that those cells will divide unchecked. And cells in fat called macrophages release chemicals called cytokines, and these encourage cells to divide, including and especially cancer cells. All right then, summarizing with some examples here, for any correlation, we must consider various other plausible causes of the correlated events or factors where one is not the cause of the other. And this is from the handout I have for you in Module 4, Chapter 10. Some of these are going to be silly or you think obviously only accidental. And again, you'd have to test these to be sure, but these are actual measured correlations. They are real associations. Now the question is whether there's any sort of real connection. Gun ownership is strongly correlated with suicide. The more we see in a population people owning guns, the more we see the suicide rate increase in that population. Being in the NBA is positively correlated with having shoe size 12 plus. The lower your socioeconomic status, the lower your overall quality of health. Have you ever noticed that being a Florida resident is highly correlated with having gray hair? I mean, it's hard to resist coming up with causal stories that explain that, but when you're looking at getting clear on the associations, describing them well enough so that you can then consider alternative hypotheses, you don't want to jump to a conclusion. You're going to start liking your explanation. Look, I'm going to go, being a Florida resident is highly correlated with having gray hair. Well, I know why that is. That's because the gray hair is the old people, the elderly, they move to Florida because it's nice and warm and it's comfortable and it's cheap, and they want to escape the snow, right? I mean, that totally makes sense, and that's why some people go there. But why are we seeing this correlation? What about other states? What else could be causing them to go there, right? I sort of, in my little story, did mention other factors. And notice that the more we find evidence that supports the story or is consistent with the story, the more we like our explanation. And that's actually a fatal flaw in hypothesis testing. Visiting the doctor is positively correlated with being sick. I mean, everybody notices this. This is why people are afraid to go to the doctor, especially we're afraid to go to the hospital. Hospital is where you go to die, right? Okay. It's also where you go when you have serious issues to get treated and cured. Oh, smoking cigarettes is positively correlated with having a heart attack among young people. Women with breast implants are 2 times more likely to commit suicide. What's up with that? Morning sickness is the sign that pregnancy is progressing well. Some say nausea and sickness are linked to a 70% reduced risk of miscarriage. So here we're seeing a correlation between nausea and sickness. That is, the more of that we see in pregnant women, the more we see a reduction in the risk of miscarriage. I mean, miscarriage is common, but it's less common in women who have morning sickness. Women who attend college are less likely to marry. I leave it to you to speculate about that. Ask yourself how you might test those hypotheses. Red meat consumption is associated with an increased risk of total cardiovascular disease and cancer mortality. This is a correlation that a lot of people don't like. This is a correlation people use to make the case that we should be vegetarians. This is a fairly robust result. It's repeated over and over, and so it does require some kind of explanation where we maybe should consider that meat consumption has something, certainly not everything, to do with people getting cardiovascular disease and cancer. All right, I want to talk now about Mill's methods. So here's John Stuart Mill. He presented several methods, here are 5, for making causal inductive arguments in his system of logic. Recall that an inductive argument is one whose conclusion is only at best probably true, so we don't criticize such arguments by saying that their conclusion isn't necessarily true. That's a deductive argument. And we have to realize that any time we say that something causes something else, it's only ever probable, it's only ever an inductive argument. So we're going to talk about these 5 methods, and they get different names, but in general I think this will capture the gist of them. There is the method of agreement, the method of difference, the joint method of agreement and difference, the method of residues, and the method of concomitant variations. And in some cases, you can use all of these. Mill's 5 methods are not an adequate or complete account of scientific methods. They are tools for discovering, considering causal factors, and rules for proving, testing possible causal relations, connections between events. Often, other relevant factors play a significant role, and sometimes causes of events have multiple causes. Remember, reasoning about causes and effects is inductive reasoning, so there are no guarantees that any presumed causal relation is actually real. What you're going to see in the text is the author going through several examples of constructing tables of factors and occurrences of those factors in subjects, in instances, and also listing on the right in a column the outcomes. And what we're doing here is trying to sort out causal factors and outcomes, searching for those factors which are implicated in events that we want to explain. So I'm going to give you some summary first before we go through some examples of those. So these tables expose necessary or sufficient conditions, or both, for phenomena. Again, phenomena are the things we observe, we want to explain. And we do this given a list of possible conditions. And again, use these guidelines when constructing those charts and answering the exercises in the text. You should go through each of the exercises in the chapter the author details. Okay, summarizing, if factor A is present in each instance of an effect you want to explain, but B is absent, then A is not a sufficient condition for B, right? Suppose you want to explain B. If A is absent in each instance of an effect, but B is present, then A is not a necessary condition for B. Now, we're going to use the method of agreement to test for necessary factors or conditions. And we'll use what's called the method of disagreement to test for sufficient factors or condition. And we'll use some combination of those two in the joint method. Okay, so there's the guidelines, and these are on the handout as well. This is what the method of agreement looks like. You look at 2 or more instances of an event to see what they have in common. So you've got 3 people who get food poisoning in a restaurant. That's what you want to explain. What are the possible causes? Well, here's what the people ate. Fish, spaghetti, ham, bread, appetizer. Some people ate some of those things. Some people ate more of those things than others. So we want to explain the food poisoning. That's your effect. So what are the possible causes or possible causal factors, to be more precise? In each case, again, all the people are sick. We want to explain why all of the people are sick. We want to explain the correlation between all the people being sick and the food poisoning. Looks like the only thing they all have in common is that appetizer. So that's implicated. Again, for all we know, there's some other factor that's not on the list, and we should be aware of that. Again, we shouldn't just like and run with and accept unconditionally it's the appetizer, although here it looks like the appetizer is the most probable cause from those possible causes available. So one criticism of this is that the method helps narrow the search for variables or factors, but it does not provide conclusive proof that we have found the cause. I mean, for that, you'd have to do something like get the people back to, it'd be hard to reproduce the circumstances, but you'd have to basically give people the appetizer and then see if they all get sick again. This method only offers partial tentative inductive evidence, but it does reveal possible necessary causal factors, right? In this case, we're describing something that occurred in the past. We want to explain the food poisoning, and in this case, it looks like the only thing all people who got sick had in common is the appetizer. Okay, so the method of difference. Again, the method of difference helps us find sufficient conditions. This looks for what all the instances of an event do not have in common, who did not get the food poisoning. And you really should consider those people who are not sick as well, right? So here's another list of suspect possible causes, possible causal factors. We want to explain the food poisoning and the 3 people, not including Kristen. We also want to explain, of course, why those people got food poisoning and she did not. So everybody ate the hamburger, but not everybody got sick. 3 people, 3 out of 4 ate the French fries. Those 3 got sick. All 4 of them drank the tea, and all 4 of them had the pie. It looks like the only relevant difference here is that Kristen did not eat the French fries. So that's looking like what explains why she did not get the food poisoning. Again, this identifies a sufficient condition as the probable cause, but does not provide conclusive proof. Again, what do you mean by conclusive proof? You're going to have to do a test, a randomized controlled trial. And in this case, since you're explaining something that occurred in the past, a unique event, all you've got is speculation. But you need to consider other possible causes. Now, you can conjoin those methods into a more powerful test. Mill called this the joint method of agreement and difference. And this gives you both necessary and sufficient conditions, which are better or more comprehensive causal stories, explanations. If 2 or more instances of an event have only one factor in common, while the instances in which it does not occur all share the absence of that factor, then the factor is a likely cause. Okay, this is a good place to just stare at this chart and see if you can recognize the pattern here. My reading this to you is not going to be helpful. You've got to understand this. So, take a closer look. We've got the instances of the effect on the left. So we've got John, Robert, Christina, Kristen. We've got all these factors, the fish, spaghetti, ham, bread, appetizer. When we put these together, we get that apparently from this, if those are the only factors we're considering, that it's the appetizer with it which is both necessary and sufficient to provoke the food poisoning. One person didn't get it, she didn't eat the appetizer. Okay, so we also want a way to describe events or outcomes that are the likely result of multiple causes, multiple factors. And so some aspects of the outcome are influenced by one or more important factors, but then there's other factors as well that explain the range of possible outcomes. So this method is going to subtract from a complex set of events those parts that already have known causes. Whatever remains is going to be the most likely cause of the remainder of the effect, right? So, real quick, we want to explain people's allergies. So it's spring, and people have, hay fever. Hay fever is what we call allergies. Your runny nose, itchy nose, coughing, perhaps asthma, and people itchy eyes, etc. It turns out all sorts of trees and grasses are producing pollen. And so while you might be especially allergic to grasses, there are also these trees that flower in spring that produce allergens. And so the combination of the two makes the effects, the suffering, the allergies, the asthma, even worse. So use the method of residues to come up with all of the factors, or as many factors as possible, to explain the severity, say, of the response. Okay, the last method is called the method of concomitant variations. So that's kind of a mouthful. The method looks for 2 factors that vary together, concomitantly, at the same time. So a correlation, again, is a correspondence between 2 sets of object events or sets of data. And so we want to sort of explain correlations. We isolate one variable, speed, and say keep others constant. So here's a little chart that's detailing the range of miles per hour that someone gets per gallon of gasoline. Miles per gallon versus how fast someone drives, 0, 10, 20, 30. And we notice that speed and miles per gallon vary together. The faster you go, the more miles per gallon. The more gasoline gallons you consume. Be careful. Every cause-effect relationship is a case of correlation, but not every correlation is a cause-effect relationship. There are several known limits of Mill's methods. Again, he proposed these. Scientists use these, but again, there are more sophisticated tests and subsequent statistical analyses, all of which comprise what we call scientific methods, we use to generate and test and justify hypotheses. Some of the major concerns are we might commit false cause fallacies if Mill's methods are applied simplistically without further testing of alternative explanations. We talked about several false cause fallacies in Chapter 3, and in the module for Chapter 3 I describe some of these in videos. Mill's methods can help reveal a necessary ingredient in causation, say a correlation. But again, they don't provide sufficient evidence of causal connection, so they're not good enough, but they are useful, especially for finding necessary conditions. And if you find all of the necessary conditions, because in case there are multiple factors involved in provoking a particular response, you've got yourself a sufficient story. Understanding the how and why of causal functions goes beyond identifying cause-effect relationships to the development of theories and hypotheses. This is the basis of scientific reasoning. I'll say more about that when I talk about scientific reasoning in Lecture 7 for Chapter 13. And what I want to do here is give you some material that's not per se in the text, but it is material I present to show the relation between the causal reasoning, the concept of causes and effects we see in Chapter 10, and the scientific reasoning we will see next. So this is going to be a brief review of material on causation, which I discuss further in my final lecture on scientific reasoning. And here's a kind of a flow chart here. We observe the world and wonder, what's happening, what's going on, why does this happen? And we invent hypotheses. We get creative and think about how these events could be related, possibly connected. We generate hypotheses which we test. And if we do many tests and we have one hypothesis, which is by and large better than others, explains more or even all of the data, we tend to then accept that as a theory where a theory is going to be a full-blown explanation and description of phenomena. Again, I'm going to say more about this, but a theory is a more sophisticated entity than a hypothesis alone. Hypothesis is a statement. A theory is a collection of statements which describes and explains phenomena. Just because you got a theory or hypothesis doesn't mean it's true. It doesn't get to be, the total causal story doesn't get to be called a theory, though, unless there have been lots of tests. We test that theory, and we're constantly testing theory. New observations challenge the theory. They should challenge the theory. And if the theory persists, then we like it more, we continue to use it. But we only use it so long as it works, right? Newtonian theories about gravity between middle-sized physical objects worked fine until we wanted to describe quantum phenomena, subatomic particle behavior, or, behavior between massive objects. So we had to amend Newton's theory. Newton's theory is technically false for quantum phenomena and for massive objects. And ultimately, after testing theories, we come up with generalizations we use to explain further examples of similar phenomena. We call those laws or laws of nature, etc. But again, I'm just going through this briefly. So I'm going to talk about this connection between theoretical and experimental science. So, theory is what you've generated by observing, speculating, hypothesizing, testing, providing causal arguments for accepting explanations, etc. There's this pattern. We have facts or alleged facts, observations. We generate hypotheses, and hypotheses lead us to produce technical solutions to problems, technical resolutions of observations. Technology itself causes us to think of new hypotheses, new ways to use the technology, new ways to explain what we see. This leads to new facts, etc. So these two aspects of science are involved in the development of new inventions, technologies, treatments. Think of it this way. Theoretical science proposes explanations, causal stories for natural phenomena, and even for phenomena generated by humans. For instance, remember from high school Mendel's theory of inheritance of biological traits, right? In the pea plant, the tall ones, the short ones, the color of the plants, etc. That's going to be a theory which is going to describe the distribution in subsequent generations of the characters or traits of the plants, the tall and short or the middle-sized plants. And in experimental science, we test those explanations proposed by theoretical science. For instance, subsequent experiments in genetics found causal factors for traits. These were identified in the past, 50, 60 years as genes, being the units of inheritance, the particles, if you will, whose information gets transferred not completely and not perfectly from one generation to the next. All right, I've mentioned inference of the best explanation as an example of inductive reasoning. I guess I'm going to say it's probably among the weakest form of inductive reasoning available. Again, analogies are also fairly weak. They're still useful. Inference of the best explanation is a way of selecting hypotheses, not so much justifying them. But the mere fact that an explanation explains is not a good enough reason to believe it, because it could be explaining and wrong. Inference of the best explanation is also called abduction. There's a history, a reason for this, but it's not important here. You can use those terms independently, or rather interchangeably. Inductive reasoning that generates and justifies hypotheses or explanations is called abduction. So inference of the best explanation then is reasoning from the premise that a hypothesis would explain certain facts to the conclusion that that hypothesis is the best available explanation for those facts so far. Again, no guarantee it's true, just that it's the best. And the best hypothesis needs to provide an explanation based on historical data. It's got to be consistent with previous observations. It's got to be consistent with and the result of current knowledge. And there's got to be a strong probability that that hypothesis is the best explanation, better than accident, better than alternative explanations. So there's this relation between hypothesis testing, experiments, and predictions. The thing about scientific theories is that they have to stand up to severe and repeated testing of hypotheses. They have to provide coherent and effective explanations. They have to provide correct predictions. They have to help us discover new facts about the world. Right, it's not a scientific theory to say that the COVID-19 vaccinations people are getting are actually causing unwanted or excessive deaths in people. So I've noticed in the media that people are observing a correlation between people getting vaccinated and people having heart attacks. Well, that's interesting. There actually is this sort of correlation. Now, that's an association, but is there a connection? Well, we have to back up a little bit. We have to realize that people, they notice salient features of their environment. Okay, what I mean by that is, yeah, we are noticing that people are having heart attacks or dying of heart attacks. And we also notice that a fair share of them are people getting vaccinated. And being critical as in creative thinking of other possible relations, explanations. And one thing that jumps out is that we know that tens of thousands of people every week have heart attacks in America. So that's kind of normal. That's the baseline for heart attack frequency. You didn't know that, but if you look it up, you'll see that that's true. And so for every person we notice with a heart attack, that's a severe cardiovascular, life-threatening, if not life-ending event, right? And we look for factors prior, and we notice that they've been vaccinated. Well, lots of people are getting vaccinated. In fact, that's the idea. We're getting vaccinated because we don't want premature death due to coronavirus, right? So we've got to test that hypothesis. And when we look closely, the apparent connection is only a statistical correlation, because we see no greater frequency of heart attacks in vaccinated people than we do in non-vaccinated people. In other words, we're seeing the normal course of events, people having heart attacks, not to say they're okay or acceptable, but we're not really seeing an increase in heart attacks. Though, of course, we notice that when a person has a heart attack, that if they had some prior experience, say a vaccine that's kind of scary to us, we don't know exactly how those work, our mind thinks together there's this connection, but there isn't. So our predictions about the effects of the vaccine need to be connected to actual correct observations. Only randomized controlled experiments or trials, tests of hypotheses reviewed by relevant experts can establish these causal connections. Multiple experimental setups bringing multiple experimental setups differing by only one variable will help to uncover probable causal relations. And here I mentioned this idea of an experimental versus a control group. You're probably familiar with this, but I have more examples of this for you later. In general, your experimental group is going to be the group that gets that one variable changed, nothing else changed, looking to see if that variable is the only relevant difference between the people, say, exposed to the factor as opposed to the people not. And your control group is going to be the group in which the variable being tested is withheld. So if you want to test that hypothesis on, this would be a statistical test. You couldn't actually do this, it would be unethical. But if you want to test that hypothesis that it's the coronavirus vaccine that's causing some heart attacks, what you've got to do is basically have randomly select several thousand people, divide them in half, and administer the vaccine to half. And they have to be blinded. They have to not know whether they got the vaccine. And then other people, maybe you give them a saline injection. That'd be your control group, okay? And you'd have to see for there to be an established connection worth researching, you'd have to see a greater number of people in the experimental group getting the heart attacks after the vaccine than in the control group. And if they're the same, there is no correlation. And without a correlation, you can't say one causes the other. So when you want to say that one event causes another, if you want to determine a causal relation, you need these 5 criteria satisfied. There should be a correlation between the cause and effect, no correlation, no cause and effect relation. The cause needs to precede the effect. The cause should be in the proximity of the effect. It should occur in space and time fairly near. A set of necessary and sufficient conditions for the outcome you want to explain should exist. You should be able to describe them, control them even. And you always have to consider alternative explanations. This is the number one place people fail to account for factors that might also be or instead be the cause of the effect you want to explain. Again, none of these 5 criteria alone is sufficient to establish a cause-effect relation. Answers to all 5 together establish grounds for a cause-effect relationship. Some details here about these criteria. A correlation is required but cannot in itself establish a causal relation, so I've talked about this. 2 and 3, the time lag, spatial distance between the cause and effect needs to be considered. The longer the time lag, the greater the spatial distance, the more the situation can be interrupted, confused, confounded by other variables. Criterion 4. This requires that X caused Y be backed by, number 1, X was sufficient to bring about Y, and X was necessary for Y. So one of the more robust theories about causation, the causal relation, is that the story should specify necessary and sufficient conditions, not just 1 or 2, but all of them that are required and together are jointly sufficient to explain whatever it is you want to explain. Number 5, ruling out plausible alternative explanations means that the evidence both refutes rival claims and confirms or supports the hypotheses. Again, confirmation doesn't prove something's true. Confirmation just says, okay, we're seeing evidence consistent with the hypothesis that's the best so far. I mean, we need a fair test here of explanations. A good test of a hypothesis involves making a risky prediction. That is, one which may show it is false if it is. I'll talk about this in the next lecture when I discuss verifiability and falsifiability. The truth or falsity of the prediction provides evidence to refute, disconfirm or falsify, or support, confirm or corroborate the hypothesis. So those are some new terms. Disconfirm, falsify, they mean the same thing. It means refute, show something's false by observation. The term confirm or corroborate is saying, say something consistent with the story you think accounts for data. Confirmation doesn't mean prove it's true. In fact, at best, you can only prove a hypothesis is false. And it continues along as long as we don't find that it makes predictions that turn out to be false. A good prediction helps us judge the strength of a causal argument. A failed prediction means the hypothesis needs to be rejected or revised. And these are the requirements for a fair test of a causal hypothesis. The prediction needs to be verifiable. It should not be trivial. It should be informative. The prediction should have a logical connection to the hypothesis. So what is a verifiable prediction? This is one where the prediction, if it is true, must include an observable event. It's going to predict something you're going to see for sure. And if you do, that is a confirmation that is going to constitute evidence that is consistent with, we say, supports the hypothesis. It isn't conclusive proof, but it's good. You don't want to not see that prediction, because if you don't, you got to reject the hypothesis. Suppose everyone in the house gets sick for no apparent reason. Why? One hypothesis: there's a high degree of radioactivity in the house. It's causing the illness. And so you predict, if you get a Geiger counter, which measures radioactive decay, if you get a Geiger counter, it's going to show high readings of radioactivity, right? So if you did see those high readings, you'd have some support for your theory that it's radiation. Of course, it could be something else still, but you'd have some support for your theory. If you didn't see the high radiation, if you saw no change in the radiation, then you'd rule that hypothesis would be dead. Hypothesis 2. Again, we want to explain why everyone in the house got sick for no apparent reason. A disease-causing ghost is haunting this house. So your prediction is there a method to obtain observable evidence? Your prediction is, I have no idea. I'm sorry. I can't think of a disease-causing ghost. How are you going to test the hypothesis that there's a ghost? You could hear the moanings and you could hear the sounds consistent with stories of ghosts. Someone could say they saw a ghost at some point. But we need a hypothesis that if we didn't see it, if we didn't see what was predicted, we would rule out the hypothesis. The problem with the hypothesis about it being a ghost that's causing the haunting, the disease, is that nothing can show it's false. It's really consistent with every observation. The thing about ghosts is, for the most part, they're invisible, uncontrollable. They come and go as they please. For all we know, they're imaginary, so there's an issue. We also want, I mentioned non-trivial predictions, where a trivial prediction is one which is, it's going to be true. And true is good, right? But lots of predictions are true and consistent with alternative, different hypotheses. So a non-trivial prediction is going to be one which is informative and not just obviously true or true for many hypotheses. It's going to be true for just one. So here I'm just saying a little bit here about Halley's Comet, and you should look this up on Wikipedia to see what this is exactly. A non-trivial prediction requires reference to background knowledge, everything we know to be true. It's got to be based on that. It's got to be consistent with that at least. So Halley's hypothesis for this recurring, I want to say comet, but this recurring sort of shooting star in the night sky, and even during daytime, Halley's hypothesis was that comets reappear in regular cycles. And background knowledge here is going to be Newtonian's theory, which we can use to describe the path through our solar system around the sun. So our prediction is going to be that a comet will reappear in 1758 in a precise location, given Newton's theory, which describes the orbit of anything trapped in the sun's gravitational pull. That prediction is going to be specific and unlikely to be true without this hypothesis. Right? So the comet's not going to reappear if they don't appear in regular cycles. So, Halley ran this risk. He says, well, we're going to see it come back at a specific time in 1758. If we don't see it, then I'm wrong. So let's connect the hypothesis and the prediction here. There must be a direct connection between the hypothesis and that prediction in order to transfer the truth value from the prediction back to the hypothesis. The mere fact that the prediction is true is not enough. You got to do a test where you run the risk of it being shown false, in which case you would reject the hypothesis. So you need to get confirmation. You need to be able to say the hypothesis is probably true. But you can only do this if it predicts what comes true on the one theory, but none of the others. Halley noticed a pattern. A comet appeared in a specific place in the sky in 1682, 1606, and 1530. And here his background knowledge is, people kept records on this. Halley speculated that they were instances of the same comet. That's his hypothesis. And if so, he could make a prediction now. Could be different comets, different phenomena, something else altogether. From this data and background knowledge, Newton's theory, Halley calculated the next return of the comet, leading to a specific prediction which turned out to be true. We can see in various years where the comet was. It's going to reappear at regular intervals along this path. Okay, that's enough of that. Here is a list of all of the exercises you should do in the chapter. I think you should do them all. Look at the answer key that I have for you. When you struggle, especially on producing those charts of possible causal factors, go back and make sure you work through the examples with the author of the text. That you have the answer key to the exercises in the text is very useful. Try yourself first, but then walk yourself through the answers and see if you can figure those out. And this is the end of Lecture 6 for Chapter 10.